Okay, in this problem, we have another spaceship. Now, this spaceship travels pretty fast. Let's draw another picture of a spaceship here. And this one is able to travel with a velocity of 2 times 10 to the power of 3 meters per second. Okay, so it can travel, what's 2 to the power of 3? That's 2,000 meters per second, or in other words, that would be 2 kilometers per second. Okay, so the spaceship traveling, what could be an ICBM, doesn't matter what it is, something like that. Now, what we want to find out is when this spaceship is viewed at rest, so let's write that down, when viewed or measured at rest, its length is equal to 100 meters. Okay? So what we have therefore is we have L naught is 100 meters. Okay? The question now becomes, how much does its length change by? So what is the delta D of the spaceship? In order to get delta D of the spaceship, now that's the change in length. I shouldn't call it delta D. Let's actually use a different, let's call it delta L. Okay, that's really what we're looking for. Sorry, L. So what we're looking for here is we're going to say, which one's longer? Well, we know that the equation is like this for the relativistic equation for length contraction. L naught multiplied by the square root of 1 minus v squared over c squared. However, we know therefore that L naught is larger than L. Therefore, we would say L naught minus L. That's going to be how much it contracts by. Therefore, that is, if we write that out, L minus L naught, we can just simply replace L with that. And so we'll go 1 minus v squared over c squared. But we know v. And if we plug that in, if we plug in all our numbers, right, it's 100 minus 100 times the square root of 1 minus 2 times 10 to the power of 3, that's meters per second, so I'm just going to leave off the units, divided by, oops, it's not cubed, that's squared, and 3 times 10 to the power of 8, all squared. Now, if we try and do this, let's see what we get. Now, this is going to be a little interesting for the calculator. We might have to do this a different way. So let's just try it first. Let's go 2 exponent 3 squared, 3 exponent 8 squared, divided by, change sign, 1 plus, which is the same as 1 minus that. Take the square root, and then let's go 100 times. Okay? And then let's go change sign, and we'll go 100 plus. And we get as an answer 2.2 times 10 to the power of negative 9 meters. Now, that is correct, but obviously there is one other way to do this. If you take this equation here and you change it into 100 multiplied by 1 minus the square root of 1 minus 2 to the power of 3 squared divided by 3 times 10 to the power of 8 squared. That's another way of doing it, depending on which way your calculator prefers, but you'll end up with the same, you should end up with the same answer. Okay, so now look at this. This is a really, really, really small number, okay? So this is, to the -9, that's a billionth of a meter. And how fast is this thing traveling? It's traveling 2 kilometers per second. That's pretty fast, 2 kilometers per second. I mean, for everyday life experiences, that's pretty fast. And yet, in terms of relativistic speeds, it's a very, very small relativistic effect. So, thanks for watching. There's your final answer. See you next time.